Hello, and thank you for your interest in our contribution to KR 2022. I'm Huifan from Beijing University of Posts and Telecommunications. Today, I will present our paper, Open Relation Extraction with Non-existent and Multi-span Relationships. To begin, our topic deals with open relation extraction that identifies an arbitrary phrase to specify a semantic relation between arguments within a context. For instance, we have a context. Researchers develop techniques to acquire information automatically from digital texts, and an argument pair, researchers, information. An ORE system would extract the span acquired from the context to denote the semantic connection between the arguments. Relation extraction is fundamental to various downstream tasks, such as constructing knowledge graphs and computing sentence similarity. Generally, the RE task can be divided into two paradigms, open and closed relation extraction. Before open RE, conventional closed RE considers only a predefined set of relation types on small and homogeneous corpora, which is far less effective when shifting to general domain text mining that has no limits in relation types or languages. Then OpenRE was introduced. However, the previous works and some widely used datasets regard an arbitrary argument pair as having a definitely existing relation by default, and constrain their task to extract a simple single-span relation between two arguments, ignoring possible non-existent relationships and flexible multi-span relations. To extend ORE for practical demands of general domain text mining, we describe the further tasks of ORE with non-existent and multi-span relations, and propose a novel query-based multi-head open relation extractor, QUORE, developed from our reconstructed datasets. Next, let me explain the task in this paper. Provided a context and an argument tuple, open relation extraction identifies a single span or multiple spans to specify a semantic connection among the arguments, or detects a non-existent relationship if the arguments do not entail an open relation. Let's have a look at some examples in Figure 1. First, the relation between Donna Karen and Long Island is a single span born in. Second, there exists no relation between a spatial comprehension and the world. Next, we have a multi-span relation, has/of, among the three arguments, Donna Karen, spatial comprehension, and New York. So how do we come up with the ideas of non-existent and multi-span relations and the proposed model? First, let's focus on the motivation of non-existent relations. Most knowledge graphs are constructed using a pipeline of named entity recognition, relation extraction with open relation normalization, and entity linking. But an arbitrary argument tuple identified from NER does not necessarily entail a semantic relation, especially when the arguments are separately distantly from each other in a long context, typically in complex sentence level or document level RE. So it is significant to facilitate models with the twofold ability to extract existing relations and detect non-existent relationships. Secondly, for multi-span relations, some languages, such as Chinese, express the relations in a flexible way of single and multiple spans. And from our observation, multi-span relations are often linked to polyadic arguments. Generally, the multi-span form represents richer and more precise meanings, playing an essential role in the diverse relations in knowledge graphs. The above two further tasks are practical and vital demands of KG construction and general domain information extraction, but neglected by the previous works. Moreover, since there are no datasets with non-existent relations, we reconstruct 4 datasets covering English and Chinese to derive the augmented ones. Lastly, we design a query-based multi-head framework (QUORE) to extract single and multi-span relations and detect non-existent relationships effectively. We are motivated by some studies on machine reading comprehension that concern extracting multi-span answers. We are also inspired by some works that design a multi-head model to solve multiple tasks. To sum up, we have 3 contributions in this work. First, we define 2 further tasks about non-existent and multi-span relations, considering the practical demands of OIE. Moreover, we publicize 4 augmented datasets and a multi-span dataset by reconstructing. Lastly, we propose QUORE model to extract single and multi-span relations and detect non-existent relationships effectively. We conduct extensive experiments showing that our models outperform the state-of-the-art method LORAN in the extraction of single and multi-span relations and the overall performances of non-existent relations. We also give an in-depth analysis of the functions of the submodules. Now, let's review some previous OIE models. We can categorize them into pattern-based and neural approaches. The pattern-based are largely based on syntactic patterns and heuristic rules that depend on external NLP tools, but they cannot handle the complexity and diversity of languages well. Meanwhile, the neural approaches typically adopt the methods of sequence labeling or span selection, but their tasks still do not consider non-existent or multi-span relations. The previous SOTA model is LORAN. However, LORAN is restricted to binary argument relation extraction and tends to output single spans rather than multi-span relations. Furthermore, based on our comparison of architectures, LORAN suffers from inherent problems in learning long-range sequence dependencies that are basic to computing token relevance to gold relations. The benchmark OIE datasets in English and Chinese include OpenIE4, LSOIE Wiki, LSOIE Science, Core, and Sauke. Their contexts are complex or multiple sentences, but the 5 datasets don't have tuples with non-existent relations. Moreover, tuples in the datasets except Sauke are in a fixed triple form of argument 1, single span relation, and argument 2. Sauke is the only multi-span Chinese OIE dataset, and there are no English datasets with multi-span relations so far. We need to clarify that the triple form take the majority of tuples in common KGs, and their extraction is the most influential part of the overall performance. But it is also important to measure the multi-span extraction ability, since the multi-span form can express rich semantics and constitute diverse relations in existing languages. Now we come to the next part, approach, and we will focus on the model framework. Given a context and an argument tuple, we first create a query from the arguments based on a template, and derive a contextual representation of query and context via a pre-trained language model, BERT. The 2 submodules of multi-head framework are SSE, single-span extraction, and QASL, query-based sequence labeling, which have different specialties in extraction. Then the multi-head selection process dynamically determines a submodule to predict depending on the input. As for the query, you may be curious about how we create it. In brief, we adopt a rule-based method to create a query template. Having n+1 slots for a possible relation with the span number up to n+1. The tokens filling a slot are separators, such as double quotes, or a placeholder for a relation span, such as a question mark. We adopt the question mark style template, taking the form of a structured argument relation tuple. We also construct other templates, but obtain marginal performance differences. Next, we will move on to the multi-head selection process. The two submodules of multi-head framework are SSE and QASL. They have different specialties in extraction. SSE is used for effective single-span relation extraction, while QASL is designed for labeling non-existent and multi-span relation sequences. Finally, our multi-head framework dynamically decides which submodule to predict depending on the input. To be specific, we utilize two feed-forward networks followed by the softmax normalization, then take each token representation from the encoder as the input to produce the probability of each token being selected as the start or end of relation span. Meanwhile, we tackle multi-span and non-existent relations with QASL. QASL utilizes the same contextual representation from the encoder as the SSE head, but it outputs a probability distribution over a set of labels for each token. In this paper, we experiment with the BIO labeling scheme. We employ a multi-head framework to handle diverse relations in single or multi-span or non-existent forms. A head is a module that inputs the contextual representation and calculates a probability distribution over predictions. In addition, we train an extra module to decide which head to use for each example. In the inference process, we first predict which head to function, then output the prediction from the chosen head. With this framework, we integrate both SSE and QASL heads, dynamically deciding which head to work based on the input and achieving different forms of relations. Let's turn to the next part, experiment. We will first talk about the experimental setup, then concentrate on the result analysis. We propose three hypotheses and design a set of experiments to examine the performances of the multi-head framework and its submodules. We choose Lauren as the baseline because it is the Salter method and the only multilingual neural model capable of processing English and Chinese text. As stated, the extraction of the triple form is the most influential part of the overall performance. So in hypothesis 1, we first evaluate on the original single-span datasets. We assume that for extracting existent single-span relations, our model can outperform the Salter method's Lauren with notable performances of the multi-head framework and the SSE model. As a follow-up to H1, we augment 4 datasets and investigate the twofold abilities of existing and non-existent ORE. So in H2, we suppose that our multi-head framework can process an input using a suitable submodule, flexibly determining whether to extract or not, and exceeding Lauren. Hypothesis 3 explores the multi-span extraction capabilities. We suppose that for a challenging Chinese ORE dataset Salker with multi-span relations and polyadic arguments, our model can effectively extract relations with a diverse number of spans. Now we come to the part of datasets and augmentation. We evaluate on 5 public datasets covering English and Chinese. From our statistics, in the first 4 datasets, a tuple is made out of a single-span relation and binary arguments. After preprocessing, we reconstruct Sauke into a dataset with single or multi-span relations and binary or polyadic arguments. To adapt the data to our setting of non-existent relations, we augment the datasets that only contain binary argument tuples. We omit to augment Sauke for the complexity of permutations of multiple arguments and the ambiguity of Chinese that an argument tuple can entail a certain relation when containing some unnecessary argument or not. We implement a rule-based augmentation method as shown in algorithm 1. In this way, we add 0 or 1 non-existent relation to each context and consider the arguments having an order to specify the direction of a relation. As for the evaluation metrics, we keep track of F1 score, precision, recall, and exact match. For existing relations, the metrics are token level. For non-existent relations, we regard the values of F1, precision, and recall as the same as exact match. Next, we will focus on the experimental results. In the experiment of hypothesis 1, we trained 3 individual models of SSE, QSL, and multi-head. To compare with Lauren, from Table 2, we observed that all the models of QURE outperform Lauren on 4 existing single-span relation datasets of English and Chinese, with notable performances from the multi-head and SSE models. We next explain the advantages of QURE over Lauren by comparing the 2 architectures. Overall, our model achieves substantial improvements over Lauren in extracting existing relations due to the better sequence representations with long-term dependencies, a basis of computing token relevance to gold relations. In H2 concerning non-existent relations, first we compare multi-head QURE model and Lauren on 4 augmented datasets. Then we provide an in-depth analysis of the functions of each submodule for data visualization. So we will first present the evaluation results on the augmented datasets and their subsets of existing and non-existent relations. As we can see, our multi-head model achieves more precise outcomes on the overall performances and the parts of existing relations than Lauren on 4 datasets. Meanwhile, Lauren outperforms on the non-existent relation subsets of LSOIE Wiki and LSOIE Science. If we focus on contrasting the partial measures between the existing and non-existent parts of the multi-head model itself, we can learn that there is this improvement space for the task of verifying non-existent relations. Next, we further probe into the functions of SSE and QSL heads in our multi-head framework by studying the data percent processed by each head and the corresponding F1 scores. From the data distributions of the 4 pie charts, we investigate the different specialties of SSE and QSL heads, and we infer that the multi-head framework can determine a suitable submodule to work dynamically based on the input data. Lastly, hypothesis 3 deals with multi-span relations. In the challenging Chinese dataset Sauke, some tuples have multi-span relations along with polyadic arguments. Next, we evaluate the multi-span extraction of QURE and Lauren on Sauke. The results from Table 4 show that our individual SSE, QASL, and multi-head models all outperform Lauren. If we focus on the extracted number of spans, in Figure 4, we discover that Lauren tends to output single-span relations, while QURE is able to generate a various number of spans dynamically depending on the input and achieve high precisions. We also conduct case studies to investigate the correct and false extractions from our model. We noticed that QURE is better at handling cases where arguments separately locate in main and subordinate clauses than Lauren. We analyzed the false cases and summarized that most errors occur in situations where the relation between arguments concerns modal verbs or auxiliary verbs. In these cases, QURE extracts either more or fewer words than gold relations. Now I'd like to end this talk with a summary of the main points. Our work targets the practical demands of ORE with non-existent and multi-span relations using a novel query-based multi-head framework, QURE. The experiments and analyses present the effective performances in the multiple tasks and corresponding explanations. In the future, we will enhance the model architecture, transfer our model to other languages, and explore the few or zero-shot learning abilities in low-resource languages and domains. Thank you. I'm happy to hear from you and your questions.